Good morning all. As I've been introduced, my name is Paul Housley. I'm a steam turbine engineer within Eon Technologies steam turbines team. For the last 3.5 years, I've been privileged enough to hold the position of subject area manager and site engineer at the new build Blackburn Meadows project. Today, I'd like to share with you just some of the challenges that presented my contract during the construction and commissioning phase. My project today will be in three areas. I will first of all talk about the project overview and a little bit about the turbine generator contract. I'll then talk about the specific challenges that we will face during the construction and commissioning. Then I'd just like to conclude the presentation with a few key factors what made the contract a success. First, a little bit about the contract. Blackburn Meadows contract was a multi-lot contract with 5 main lot contractors. The turbine and generator lot was presented by TGM Turbine. They have their offices out in Germany and Nuremberg, with their manufacturing facilities out in Brazil. The boiler and balance of plant was provided by Andrix, who were Austrian based. The fuel handling was by a UK company, Geo Robson & Co Conveyors Limited. The high voltage contract was provided by ABB from the Stone division, and the civil contract was concluded by BAM Nuttall, who also undertook the role of principal contractor. A little bit about the project timeline. I joined the team in June 2011, where my first task was to finalise the contract prior to contract signing in November of that year. A few key dates throughout the project. The first major construction component was the turbine table in August of 2012, and the TGM site team turned up in April 2013 and began the installation of the turbine generator set. Steam to set was on the 11th of June 14, a date that I just stick in mind because my wife had our final child on that week of the spinning of the turbine. And then going through reliability runs, guarantee tests, and finally handed over in August of 2014. A little bit about the plant layout. As you can see, it's quite a nicely compact site. The Blackburn Meadows power plant is a biomass-fired station. It burns waste wood delivered from a 50-mile radius. The wood is delivered to the site via heavy goods vehicles through 2 unloading bays under the road unloading. From here, we can transfer the fuel via transfer towers 1 and 2 to either the fuel store, or if needs be, we can direct the fuel directly into the boiler. The boiler is in the orange cladding in the centre of the picture. If you drive north past the motorway, you will not have seen this cladding yet, and it's still to be erected on site. In my opinion, the building behind, the most important one, the turbine building, which houses the TGM turbine generator set. And behind this, we have a district heating building. This plant has the capability of providing 25 megawatt thermal district heating capability into Sheffield. This taps into the existing Veolia network. And this plant is being commissioned as we speak and should be up and running within the next weeks. At the back of the plant we have an air-cooled condenser of 5-cell arrangement. And then to the right of the plant we have the control room, administration block and the stores. But a very nicely compact site. A little bit about my contract, the turbine generator set. It's a TGM Turbine CT5085 condensing steam turbine. It's of a single cylinder arrangement. High pressure steam is emitted through a single ESV and 2 control valves. Within the machine we have 27 stages in the high pressure region and 3 stages within the low pressure region. We have 3 uncontrolled extractions on this machine and a vertically downwards exhaust to the air-cooled condenser. The machine spins at 4,800 RPM, and this speed is transmitted through a reduction gearbox provided by Rank to the 1,500 RPM half-speed generator. The generator is provided by ABB. It's cooled via a closed-circuit cooling water system. Not only does this cool the generator, but it also cools the lube oil system, the main boiler feed pump, and the ash screws. TGM was also responsible for providing the turbine lube oil system, and the Glanstein condenser, and the turbine control system, which comprises a Step 7 system for the steam turbine and a Siemens PCS7 for communication with the plant. A little bit about the steam conditions for the steam turbine. We have 82 bar 487 inlet pressure. As I've mentioned before, we have 3 uncontrolled extractions. Bleed number 1 goes to the aerator, bleed number 2 to the district heating building, and bleed number 3 to district heating and the LP preheater. The district heating building has 2 tube and shell heat exchangers where we can configure the arrangement between bleeds 2 and 3 depending on the heat requirements required by the City of Sheffield. Exhaust conditions, we have a design case of 80 millibar. Now, as with many projects, there are challenges, and my contract was no different. This table here presents just a handful of the challenges that presented us. For today, I've just decided to focus on 3 main construction challenges, and I'll talk about one of the major commissioning elements. Right, the first major challenge to present the contract was actually on day 1 of arrival of the steam turbine. On investigation of the transport, when it arrived into site, it was noted that the support structure that held the turbine, you see the support structure here in green, was not actually in contact with the steam turbine. On a closer investigation, we could see that this was down to the wooden support frame itself. It got wet and it bowed. And after this really raised initial concerns to whether there was any damage internally to the machine. It was unclear at this stage when this damage had happened, if it happened in Brazil, during the transport, or in the UK. It was then elected at this point that the OEM contact their insurance company, and the insurance engineer arrived on site and inspected the damage. And the decision was then made to lift the machine. This then rolled into our second challenge of that week. When we were lifting the steam turbine, it was noted, the bottom and right picture here, that the LP case only was lifting. So it was feared that the steam turbine casing was deflecting between a low pressure and a high pressure cylinder. The lift was aborted and the manufacturer in Brazil contacted. It transpired that the incorrect lift information had not been sent from Brazil to Nuremberg and to the lifting contractor. So when we were trying to lift with a 4-point lift, we should have been lifting with a 6-point lift. What can we learn from this? First of all, we didn't send an engineer to do a witness or a site inspection of the machine before it left Brazil, where this support issue may have been identified. There was questions on the QA of transport from the factory to the docks to the boat to the UK and to site. And this may have led to us avoiding this situation. And in the future regarding the lift, if we could have our time again, we would have specified a lifting beam which would have removed all doubt on the lift. However, because there was an unknown quantity that we didn't know whether there was any damage within the machine, it was decided that we'd have an unforced outage and open the steam turbine. On first removal of the bearings and installation of the shaft raising gear, it was found that the shaft would not raise, and it was feared that it was wedged, fueling belief that there was actually damage internally to the machine. After discussions with the site team, it was elected to put a hydraulic ram under the shaft and slowly lift the shaft to see if it would move. The shaft did move, which then drew our attention to the actual shaft raising gear was actually incorrectly designed for the shaft. We must admit this is the first time that I've seen this, and many other civil rail engineers have seen this. So the actual shaft was deflecting. So we had a more meatier shaft built, and the shaft lifted, and we could do the clearance checks as intended. After this, we opened the machine, and to our relief, there was no damage caused by the incorrect support or incorrect lift. But what did transpire was when we were doing the alignment check, it was found that the actual figures we measured on site did not match that of the factory build figures. So the opportunity was taken, we had a discussion with the OEM, and the machine was then realigned, the carriers moved, and set in accordance with what the OEM as-built figures should have been. The machine was then rebuilt. Lessons learned from this challenge. Again, if we could have sent an engineer out to do the witness of the alignment, this misalignment error would have been identified. At the same time, while it was there doing the alignment, we could have then checked on the packaging, and the first issue may not have arose. The second main challenge really of the contract was one of the first erection activities. Once the steam turbine was erected on the turbine table, the first section to be installed was the turbine exhaust transition section. Now this converts the rectangular duct to a circular duct to allow connection to the ACC duct. So on installation of the ACC duct provided by GEA, the spring supports below the duct were released, and there was a noticeable change in the alignment of the steam turbine. Focus was drawn to the attention to the spring pots below the steam turbine duct, and it was found that the supports were sitting out of position and exerting an upward force on the steam turbine. The decision was made to, at that point, just check the calculations on both the ACC and turbine manufacturer. The turbine manufacturer at the exhaust had force of the moment limits, as with any steam turbine. However, these limits were at the rectangular duct. The contractual termination point for the contract was at the circular duct. Therefore, the mass of the exhaust duct itself was not taken into consideration with the calculation. So what did we do to rectify this? And we actually welded supports below the air-cooled condenser duct, removed the spring pots, and we took them down to Lysiga, recalibrated them and reinstalled them. However, we needed to prove to the turbine manufacturer that the forces on the steam turbine had not been reached. Now, this was not able to be done by physical measurement, and we had to do this only solely by calculation. What can we learn from this? There are kind of two things. Tie up the termination points in the contract with the OEM manufacturer. See, the turbine was from Brazil, so that was one package of work. TGM Carnissen in Nuremberg provided the exhaust duct, so their contractual termination points were slightly different. So in future, we need to ensure that any items like this are married up. But the erection sequence could have been slightly different. In future, if we actually install the exhaust transition section onto the air-cooled condenser duct first, place it in position, then we can actually set a rig up and actually do a physical measurement of the loads by pulleys and load cells, therefore proving the loads are within the limits of the steam turbine manufacturer. Moving on to commissioning, one of the first items that when we ran up, we had a slight challenge with the lube oil system. I'd like to explain first of all how this system of this machine works. We have a main shaft-driven oil pump, an auxiliary oil pump, and a DC backup emergency pump. Now, on first startup, both the auxiliary oil pump and main shaft-driven oil pump are running in parallel. When the machine reaches 95% speed, the auxiliary oil pump cuts out, and the shaft-driven oil pump should provide enough flow for the entire system. However, during run-up, when both pumps are in parallel, we had severe vibrations within the lube oil system. These were visual. You could literally see them moving 10 or so mil. So the decision was made to abort the start. We sat down with the OEM and had a discussion. We ran the machine again, and the same vibration occurred. At this point, it was decided to stop, remove the main shaft-driven oil pump to investigate if there was any damage to the pump and any other aspects within the lube oil system. Initial thoughts were to aeration in the tank, or as I said, any damage within the main shaft-driven oil pump. So the pump was removed, and I worked with the manufacturer. We stripped the pump down. There was no damage present. There was no irregularities within the oil system. So what actions did we take? When the machine was rebuilt and run, we decided to take a flow measurement survey to ensure that the flows of the system matched the design from the turbine manufacturer. Obviously, we removed the pumps and did an inspection, which revealed no damage. We introduced the OEM introduced additional vent lines to see if this was the root cause of the problem. And then on our guidance, we installed a sight glass so we can actually physically see what the oil was doing, which gives a good indication if there's any air within the oil. But during the removal of the main driven oil pump, so we could keep forward momentum with the project, which is one of the main things that you have to do, and we just introduced a spool piece, which allowed us to run the plant on the auxiliary oil pump with a DC backup only. And this becomes quite a nice strategic spare in the future. If there are any problems with the main shaft-driven oil pump, we can simply replace it with this and keep operating. The machine was rebuilt with the new vent lines, confidence in the main shaft-driven oil pump. However, the severe vibrations remained, so the initial action did not resolve the problem. So we had to take a step back further and go back to the design and start scrutinising the design drawings and the philosophy of the system. And it actually transpired that the error occurred in the drawing office back many years ago. What we have is return lines to the oil system. Many of the return lines are not fully charged, as many of you are aware, and when the oil goes into the tank, we have aeration holes. However, we have a main spill line, so when both pumps are in operation, any excessive oil is returned back to the tank. However, this pipe should not have had these holes in. Now, on the manufacturing drawing, the holes are clearly present, so they were actually manufactured and installed. And when the pressurised oil was returning to the tank, it was kind of acting like a Venturi effect, aerating the oil. And the position within the tanks meant that the residence time was too short. And that was decided that was the root cause of the excessive vibration. With this in mind, how to fix it, we came up with a very simple clamping mechanism to blank off the holes. This is only a short-term measure. At the first major outage, hopefully we'd take this pipe out and have a new pipe welded in. The system was rebuilt and the vibrations disappeared. What can be learnt from this? Well, if we did a factory acceptance test, would we have seen this? Would we have met this? If the SQS engineer was out there, he would have taken a site drawing and compared it against an as-built piece of equipment, and the two would have matched. So I would say that this one would have slept through the net even if we had inspected the tank, unless you've got a specific knowledge of a system of this type. Now, they were just a snapshot of a couple of the challenges that faced the turbine generator contract. They were unforeseen. But what made the contract a success, kind of following on from the theme of the two gentlemen before me, it's really identifying and managing the risk. Now, within our site team, we had a very useful tool, as many people do, as a risk register. And each month I would sit down with the assistant project manager and go through the risk register. However, this is only a good tool if the information you provide to it is accurate. How to provide this with accurate information? Well, as the site engineer role, it was my job to be out on the site, and from an early outset, not only building relationship within the core team, it's building a relationship with my OEM contractor, the other lot contractors, being involved on a daily basis in the morning meetings, evening meetings, being involved with the subcontractors doing the work. And slowly over time, you can build up a network of communication. This allows me to always be informed of the situation. Contractors will come to myself, we could get involved and identify potential risks on a daily, weekly and monthly basis. This could then get fed back into the risk register. We could sit down, evaluate the cost. This could be presented to the PM. And at the end of the project, I was quite proud because the risk register actually married up with the actual cost at the end of the project, showing that the process actually worked. But it was the constant review. So that was kind of identifying it and recording it. But managing the risk, it was very important. The network of engineers and specialists that I built up during the contract, and I was fortunate to have world-class engineers on speed dial to the phone back to Eon Technologies, and we were able to sit down with the OEM, present solutions to them, work together, and then we could win together. It's a philosophy that I stood by, and it transpired over the last 3 years. So they were just some of the key fundamentals that made the contract actually a success. But underpinning really to this success was being proactive in safety. Now, from a very early outset, I know a lot of people are going about safety first, but from a very early outset it's very apparent that the non-UK contractors are not very familiar with the UK regulations and obligations when working within our country and on our sites. So from an early outset it was decided that I would take a very much active role with the OEM, with my contractor. Obviously, I had prior experience from my Nebosh construction, previous testing days, permitry experience. So I was able to sit down with the OEM, work through their health and safety, work with their safety advisor, educate them and advise them how they need to document and work within our site. It was really taking charge and responsibility. On many contracts, yes, you can wait for a mistake to happen and use this as ammunition in many meetings. But this is not proactive and it does not keep forward momentum. So to keep this forward momentum, there was very much a philosophy not only on my contract but throughout the project of taking charge, don't wait for a mistake to happen, be proactive and deal with the situation. And one thing we did pride ourselves at Blackburn Meadows with, we were one as safety. We worked very closely with the principal contractor, with the Eon and the lot contractors teams. We had regular daily safety walk-rounds. Each week we would review other areas' works and work together. We did have our difficult times, yes, and we did have some shortcomings within the safety area, but we worked through that, and I think as a project team we were very proud of our safety at the end of the day. But lessons learned, we could have actually been a little bit more specific within the contract, especially with the non-UK contractors, of exactly what their requirements are, what legislation they need to work to, what qualifications they must have when coming through build and commissioning, what regulations and rules that we want them to work to, and be very specific in the contract. Not a few lines, it should be in a table, you shall work to this, you shall work to this. And I think this would have ironed out a lot of the issues that we faced. One very brief safety lesson that we learned in the contract, we said you need to have a safety passport to come onto site or equivalent. The word or equivalent caused quite a lot of trouble. As a result, a lot of the UK contractors could work, but the non-UK contractors had to go on to training courses just to get on site to use equipment that they've been using the week before in Germany or the week before in Italy. Things like this could have been ironed out before they even stepped on site and helped with the momentum of the project. But at the end of the day, I would say I was very proud to work on the project, taking it from contract through to handover. We took it from this turbine delivery onto site. This would have been better with music, but I wasn't that talented. Through a cold commissioning, and then through a hot commissioning, through all the challenges, a few that obviously I've mentioned. To success. There we go, that one worked. Okay, I'm very proud. We did actually have a zero safety improvement notice for my contract, something that my counterparts didn't. Demonstration tests were all passed. The guarantee test was passed with margin to spare. Handover was completed on time for the turbine contract and indeed for the project. And the budget, commercial, was satisfactory, not only for the turbine contract but for the entire project. Now I'd like just to finish the presentation by saying it's an invaluable experience working on a new build project, and I would urge anyone that's not had that chance to do so. I was a very different engineer when I started, and I'm a very different engineer now I have finished. It's been a very valuable experience, and I do look forward to any of your questions, and I can bend your ear all night about Blackburn Meadows, so please come and see me. Thank you.